Hello friends, myself Dr. Ansari Farzana from Chemistry Department, J.A.T.rts Science and Commerce College, Malegaon. As we have seen something about the chromatography in the previous section, chromatography are generally divided into two parts: partition chromatography and adsorption chromatography. Partition chromatography and gas chromatography belonging in the both cases partition chromatography and the adsorption chromatography. High performance chromatography, high performance, or you can say that high pressure liquid chromatography is the branch of gas chromatography. High performance chromatography was developed to overcome the ineffectiveness of the gas chromatography because of the thermal instability of the solutes during biochemical analysis. Gas phase separation and the analysis of very polar high molecular weight by biopolymers was impossible by using gas chromatography. As a result, alternative methods were hypothesized, which would soon result in the development of the high performance liquid chromatography. Following on the seminal work of the Martin and Sainz in 1941, it was by Carl Gidding, Joseph Haber, and others in the 1960s predicted that liquid chromatography could be operated in the high efficiency mode by reducing the particular diameter of the packing material of the column below the typical LC liquid chromatography and gas chromatography level of the 150 micrometer. The speed of the mobile liquid phase can also be increased by applying high pressure. This prediction underwent extensive experiment and the refinement throughout the 60s into the 70s. Early developmental research began to improve liquid chromatography particles and the invention of the ZPAX, a superficial porous particle, was promising for high performance liquid chromatography. The 1970s brought about many development in the hardware and instrumentation. Research began using pump and the injection to make a rudimentary design of the HPLC system. Gas amplifier pump were ideal because they operated at constant pressure and did not require leak free seal or checked wall for steady flow and the good quantitation. Hardware milestones were made at the DuPont IPD industrial polymer division, such as replacing the septum injector with the loop injection wall. Paper chromatography. Paper chromatography, this is the liquid partition type of chromatography. This old technique is used to analyze complex mixture such as ink by separating the different chemicals it was made from. The method involved placing a small spot of sample solution on a strip of chromatography paper. The paper is placed into a jar containing a shallow layer of solvent, that means mobile phase, and sealed. As the solvent rises through the paper, it meets the sample mixture, which start to travel up the paper with the solvent. Different compounds in the sample mixture travel different distances according to how strongly they interact with the paper. mixture of the different characteristics, that means size and solubility, travels at different speeds. This allows the calculation of RF value and can be compared to standard compound to aid in the identification of an unknown substances. Thin layer chromatography. Thin layer chromatography is also called as TLC, is a widely employed laboratory technique and is similar to the paper chromatography. However, instead of using a stationary phase of paper, it involves a stationary phase of a thin layer of the adsorbent like silica gel, alumina, or cellulose on a flat inert substrate. Different compounds in the sample mixture travel different distances according to how strongly they interact with the adsorbent. This allows the calculation of an RF value and can be compared to a standard compound to help in the identification of unknown substances. Compared to the paper, it has the advantage of faster run, better separation, and the choice between different adsorbent. Ion exchange chromatography. It is just like a column chromatography. Ion exchange chromatography is a column chromatography based on charge. The stationary phase is usually an ion exchange resin that carries charged functional group which interact with the oppositely charged group of the compound to be retained. It is used to separate charged compound including amino acid, peptides and proteins. Ion exchange chromatography separates molecules based on their respective charge group. Ion exchange chromatography retain analyte molecule on the column based on the coulombic ionic interaction. The ion exchange chromatography matrix consists of positively and negatively charged ions. Essentially, molecules undergo electrostatic interaction with opposite charge on the stationary phase matrix. The stationary phase consists of immobile matrix that contains charged ionizable functional group or ligand. The stationary phase surface display ionic functional group that interact with the analyte ion of opposite charge. To achieve neutrality, these inert charges couple with the exchangeable counter ion in the solution. Ionizable molecules that are to be purified compete with these exchangeable counter ions for binding to the immobilized charge on the stationary phase. These ionizable molecules are retained or elevated based on their charge. Initially, molecules that do not bind or bind weakly to the stationary phase are first to wash away. After altered conditions are washed away. Altered conditions are needed for the elution of the molecule that bind to the stationary phase. The concentration of the exchangeable ion which compete with the molecule for binding can be increased or the pH can be changed. A change in pH affects the change on the particular molecule and therefore alter binding the molecule, then start eluting out based on the changes in their charges from the adjustment. Further, such adjustment can be used to release the protein of interest. Additionally, concentration of the counter ion can be gradually varied to separate ionized molecule. This type of the illusion is called gradient illusion. On the other hand, step illusion can be used in which the concentration of counter ion are varied in one step. This type of chromatography is further subdivided into cation exchange chromatography and anion exchange chromatography. Positively charged molecule bind to the cation exchange resin, while negatively charged molecule bind to the anion exchange resin. The ionic compound consisting of the cationic species, that means M plus, and anionic species, that means B minus, can be retained by the stationary phase. Cation exchange chromatography retain positively charged cations because the stationary phase displays a negatively charged functional group. See here the equation RxC plus, it is the resin, plus M plus B minus, these are the ions of the solution which is to be separated, and this M plus exchange with C plus, that means it gives us Rx M plus and C is releases as C plus and B minus. Anion exchange chromatography retain anion using positively charged functional group. In ion chromatography, the interaction of the solute ion and the stationary phase based on their charge determines which ions will bind and to what degree. When the stationary phase feature positive group which attract anion, it is called as anion exchanger. When there are negative groups on the stationary phase, cation are attracted and it is a cation exchanger. The attraction between ion and stationary phase also depends on the resin. Organic particles used as an ion exchanger. Resin, often termed beads of ion exchange chromatography, may include functional groups such as weak or strong acid and weak or strong bases. These are also special columns that have resin with amphoteric functional group that can exchange both cation and anion. Some example of functional group of strong ion exchange resins are quaternary ammonium cation, which is an anion exchanger, and the sulfonic acid, which is an cation exchanger. This type of the cation exchanger can maintain their charge density over pH range of 0 to 14. Example of functional group of weak ion exchange resin includes diethyl amino ethyl, which di, diethyl amino ethyl, which is an anion exchanger, and carboxymethyl, which is cation exchanger. These two type of exchanger can maintain the charge density of their column over the pH range of 5 to 9. There are various applications of ion exchange chromatography. Ion exchange chromatography is commonly used to purify any kind of the charged molecule, include large protein, small nucleotide, and amino acid. Today, ion chromatography is important for investigating aqueous systems such as drinking water. It is a popular method for analyzing anionic element or complexes that help to solve environmentally relevant problems. Thank you for watching.